Hey there. So this video is about the Bolzano-Weierstrass theorem, and basically I have two goals in making this video. The first goal is of course to give you a proof of the Bolzano-Weierstrass theorem, and the second bigger goal is to sort of get rid of all the negative ideas you might have about real analysis. For example, some students think that it's very overly pedantic, and what you basically do in real analysis is prove sort of obvious statements which in ways which are very complicated, and they have an unnecessary focus on detail, and they don't really connect to the visual way of looking at things. So I basically want to get rid of all those ideas of real analysis you might have and show you that intuition actually plays a big role in real analysis, not only in figuring out what to prove but also in how to prove it. And for demonstrating this, what I'll be doing is going about this in a sort of pop math way, where I'll basically give you an outline of a proof which can be made rigorous very easily if you have the right tools, but even someone who doesn't have knowledge of, let's say, basic calculus should be able to understand it and understand the statement of the proof, obviously, and also understand the proof and sort of why it is a valid justification of the statement. So to begin with, I will introduce some definitions and ideas which are required to even understand the statement of the proof. So the first one of them is what it means for a set to be bounded. So when you have a subset of the real numbers, I basically want you to think of it as some piece of the real number line. So you have the real number line, and by some piece I don't necessarily mean a continuous piece like this. It can also be broken apart sort of. So for example, you can have something like this. So I can reasonably say that this whole thing put together is a subset of the real numbers, which I'll denote by S. So that is written as S subset R. So what it means for a subset of the real numbers to be bounded is basically that it shouldn't extend to infinity in either direction. Now again, extending to infinity doesn't necessarily mean that you have sort of a point over here and then the entire real line from here onwards is in S. So this is not the only way in which S can extend to infinity. It can also extend to infinity like this. So you have a point here, and so on. So they can basically be equidistant points which are sort of placed well apart. So this is not continuous by any sense of the word, but it does extend to infinity. So basically when we say bounded, we mean it doesn't extend to infinity, or for that matter in the opposite direction to minus infinity. In other words, you can say that there is some point, let's say over here, which is to the right of everything in S, and likewise there is some point over here which is to the left of everything in S. And the second thing which we need to understand is the idea of limit points. So what does it mean for a point to be a limit point of a set? So by that we basically mean that if you have a point over here on the real line, then no matter how close you sort of zoom in on this point, there is always something from S which is in that zoomed in part. So for example, so this is your point P, which you want to check whether it's a limit point or not, and let's say this is a point in S, and this is a point in S, and this is a point in S, and so on. No matter how close you zoom in, there is always some point of S which is in the neighborhood of P. So again, I drew them as sort of distinct points, but it doesn't have to be that way. It could also be that you have a sort of continuum of S which is close to P. So another thing is that it is not necessary that if you have a limit point of a set, it must be in that set. So for example, if I take the open interval from 1 to 2. So what open interval basically means is that I have 1 over here, I have 2 over here. So this set is basically everything which is strictly in between 1 and 2, but not 1 and 2 themselves. So the way we denote that usually is we'll write 1 over here and we'll draw a round bracket around it. So maybe I drew it too small. So this is how you would denote an open interval. So this point is 1, this is 2, and this round bracket is basically saying don't include 1 in your set, include everything after it, and this is saying don't include 2, include everything before it. And likewise, what if I want to include 1 in my set? Then we basically do this. So now the square bracket indicates that you have to take that point in the set, and the round bracket again indicates you don't have to take it. So if I do this, then this basically means that everything which is after 1 as well as 1 itself is in the set, and everything which is before 2 except 2 is in the set. So that is sort of the setup of, like, those are the required definitions for the setup of the problem or the theorem. So the theorem basically says that if I have a bounded set of real numbers which has infinitely many points, it must have a limit point. So I'll write it down. So if S is a subset of the reals and S is bounded, then S has a limit point. And this is the Bolzano-Weierstrass theorem in one dimensions, and this is just a version of it. There's also a version which talks about bounded sequences, but I will not go into that right now. So this is the Bolzano-Weierstrass theorem. So firstly, I want you to understand the sort of intuition behind this statement. So it's basically saying that you have a bounded subset of the real numbers. So since it's bounded, we know that there are 2 points in the real numbers such that all of S is contained between these 2 points. So there is no point of S over here, for example. It's all contained between these 2. And you are also told that S has infinitely many points. I didn't write that down. S is bounded and has infinite points. So firstly, you must understand that you can have infinitely many points in a bounded region. You don't necessarily have to go out to infinity for having infinitely many points. For example, if I just take the closed interval between these 2 points, then this does have infinitely many points, because we know that in any stretch of the real numbers there are infinitely many points. So this is an example of a set which has infinitely many points and it is bounded. So let's see if it satisfies the statement of the theorem. Does it have a limit point? Well, yes it does, because for example, if I pick this point, then no matter how close I zoom in on it, there is always some part of S which is in the neighborhood of that point. So how do we prove this in general when we don't have a sort of nice image of S in our head? So first let's imagine what it will feel like to try to fit infinitely many points in a bounded region. So the first point I might put somewhere near the center, and this might be the second one, third one, fourth. Now what I'm sort of seeing is that no matter how hard I try now, the next point which I draw is going to be pretty close to at least one of the previously drawn points. For example, I might draw it here, but then it's very close to this one. I might draw it here, and then it's very close to both of these, and I might draw it here, in which case it's close to both of these. So as I keep putting more and more dots in this bounded region, it is obvious that they will have to start coming close to each other in some place. So it could be that there are sort of multiple hotspots where these points are coming together. So you could have something like this. So the points are really close together over here, and they are really close together over here, but they are pretty sparse everywhere else. So these are sort of hotspots, and if you were looking for a limit point, then these are the sort of places where you would expect to find one. And another case is that it has only one hotspot, and the rest is pretty sparse. But yet another case is something like this, where basically the entire thing is a hotspot, because everywhere, no matter how close I go, how close I zoom in, there are always infinitely many points. So how do we figure out which of these cases S falls into? And since none of that information is given in the statement of the theorem, so if we want to prove the theorem, then we sort of need to figure out a method to figure out which of these cases S is. So how do we do that? And a better question would be, do we even need to do that? Or is it just that our visual intuition is sort of misleading us into thinking that the type which S falls into is somehow important? So here's what I'll propose. Look at the smallest element of S, or rather I would say the smallest element which is below or to the left of all of S. So in this case, the smallest element of S would be this one. We know that this is a square bracket, so this point must be included in S. And likewise over here, the smallest element is this, here it's this, and here it's this. But for example, if I had a case where this was open, so this was a round bracket, then this point is not included in the set, but we'll still call it the smallest element of the set, even though if it is not in the set, because it sort of fits into that idea we have of the smallest point, the best fit sort of point, which is to the left of S. So formally you would call this the infimum of S. And for those of you who want a formal proof, we know that the infimum exists because S is bounded by definition. So now we have the sort of smallest element of the set. And now in these two cases, what happens is this point itself is a limit point, because no matter how close I go to this point, there are always points in its neighborhood. So over here, this entire region is there, and over here, this entire region is there. So in both of these cases, that smallest point itself is a limit point. Over here though, that's not the case, because this point is pretty isolated. So I can, for example, zoom into this region around it, and there's no points of S in its neighborhood. So this is for sure not a limit point. And likewise, this is also not a limit point, this is also not a limit point. So what we do is, we take this, so if this is the case, then we are done. So this is a limit point, and we have shown that S has a limit point, so we are done. Over here, we are not yet done. So what we do is, we remove this point from S, and we go to the next smallest one. And again, by smallest, I basically mean the infimum. So if you have this sort of case, you know what to do. So now that will be this point. Over here, it will be this one. Over here, it will be this one. And once again, in none of these cases is this the limit point, and likewise over here. But what you now notice is that if I keep doing this, I keep removing these points and taking the next smallest one. So I've removed all of these which weren't limit points. So now I go to this one, this is also not a limit point, go to this one, and so on. So if I do the same thing over here, then you can see that I am sort of guaranteed to converge on a hotspot, because if there is a sparse region, then in finitely many steps I should be able to eliminate all of those points as not limit points and get to some hotspot. So that is basically the idea of the proof, that if you have a sparse region where there are no limit points, then in finitely many steps you will eventually end up crossing that region and you will end up beyond it, and hopefully you will find a hotspot beyond it. So how can you be sure that you will find a hotspot beyond it? So here's where we use an idea from the convergence of sequences. So what we need is the idea that if you have a sequence which is basically a sort of discrete set of points, so which is ordered, by the way. So let's say this is the first point, second point, and this might be the third point, so it doesn't have to be strictly increasing, and this might be the fourth point, and so on. You get the idea. So this is basically what a sequence is, and the claim is that if you have a strictly increasing sequence, which is basically a sequence where a point which has a higher label is also to the right. If you have a strictly increasing sequence which is also bounded from above, then it must have a limit point. So for example, now once I have gotten this close to this upper bound, then I have to still fit infinitely many points in this region, right? And they have to all keep going to the right. So either I can start making a hotspot sort of before I even reach this bound, so somewhere over here for example, or I can just keep going and make this bound my hotspot. But in either case I must have a hotspot. So for those of you who want a rigorous proof, I guess you probably know this fact that if you have a strictly increasing sequence which is bounded from above, it must converge. So now what you notice is this is actually a strictly increasing sequence, because if I make a better diagram, so what we were sort of doing was, so I'll draw an S, an example of S, and let's say there is a hotspot over here, but we don't know that. We have to sort of figure that out. So this is my first element of the sequence, which is basically the smallest element of S, but I see that it's not a limit point, so I remove it from S, and then I go to the next one. Again I see this is also not a limit point, so I get rid of it, and I keep doing this until I start converging at the hotspot, which is, let's say, over here. And now at this hotspot I must have sort of infinitely many points in this region. So if I label this as 1, 2, 3, 4, 5, 6 and so on, then this is basically a strictly increasing sequence. So for those of you who want a formal proof, basically I take inf S as, let's say, the first element x1, and then x2 is the infimum of S minus x1, and then x3 is the infimum of S minus x1, x2 and so on. So what we have now sort of guaranteed is that if there is no such interval which happens to be in S, and S is sort of discrete points like this, then we can just keep taking the smallest element of S, then remove that, take the next smallest, remove that, take the next smallest and so on, and we'll have a strictly increasing sequence which is bounded from above because S is bounded. So this sequence must converge and we have constructed a limit point. Otherwise what happens is you have a sort of, either you have such a scenario where the first element, the first smallest element which you take itself is a limit point, or what happens is that you have a sort of mix of the two cases, which I haven't talked about yet. So in the mix of two cases, what you will basically have is some discrete points over here which are, let's say, sparse, and then you have an interval. So now what will happen in our algorithm is that you'll go to the smallest element, it's not a limit point, next smallest, not a limit point, next smallest, not a limit point, not a limit point, and now you have hit a limit point. So once you hit a limit point, you can stop. But if you never hit a limit point, then you're sort of going, you're picking infinitely many points which are strictly increasing, bounded from above. So the sequence must converge and you have constructed a limit point. So that is basically the proof. And if you want a proper rigorous proof with sort of no hand wavy stuff and like everything properly sketched out, then there is a link in the description which will take you to a PDF which is basically a write-up of this idea. So if you want a rigorous proof, check that out. If you are happy with this, then that's great. And I would suggest that if you do want a rigorous proof, you first try to use this idea which I have given you and sort of write a rigorous proof of your own. And if you can't and you need some help, then you can leave a comment and maybe I'll give you a hint based on where you currently are and where you are stuck. Or if you want, you can just go to the PDF and read the proof for yourself. And that's it for this video. Thanks for watching. There will be more videos coming out soon which will be on the Heine-Borel theorem and higher dimensional versions of Bolzano-Weierstrass and Heine-Borel. So very fun stuff, and hopefully I'll try to make them as accessible as I can. Like I said over here, at least my goal was that even someone who doesn't have introductory calculus knowledge should be able to understand this idea and appreciate what's going on, even if they don't understand the details like the infimum moments, so on. So hopefully I achieved that goal. Let me know in the comments, and I will try to achieve that goal as much as I can in the upcoming videos as well. And thanks for watching.
Thank you for watching.